In this example, we have two charges, Q1 and Q2, which are both positive but are of different magnitudes. We have decided to find the total field at the point P. Don't be confused that Q2 is closer but is exerting a smaller field. Q1 must be a bigger charge than Q2. So to get the resultant field, we add the vectors E1 and E2. Remember, to add vectors, you can lay them end to end, so we end up with this as the resultant field, magnitude and direction. And this is the equation for adding the electric field from multiple charges, where n is the number of charges that you have. So in this case, n equals 2, so we do the summation for I equals 1 and then for I equals 2. And what direction will the R1 unit vector be in this case? That will be from the charge to the point. We can also write the vectors in terms of the vectors from the origin, which is probably how you will come across them. So now, using Q1 as an example, to get from Q1 to P, we go the wrong way along little r, i.e. minus it, and then the right way along big R, i.e. plus it. To write the unit vector in terms of vectors from the origin, we would just have the big R minus little r to give the correct direction. Then we would have to divide by the length, or the modulus, of big R minus little r to make the size of the unit vector equal to 1. So the unit vector would look like this in terms of vectors from the origin. Now, if we expand this from two charges to a continuous charge density of ρ throughout a volume V, then we need to split the whole volume up into essentially lots of point charges and add up the electric field from each tiny chunk of that volume, i.e. integrate. The charge from one of those tiny chunks of volume will be ρ dV. So the charge density, the charge per volume times the volume will give the total charge in that tiny chunk. So we then have this as the equation for the electric field from a tiny chunk of volume at the point R. We're now calling the point R just to be more general. So we have the distance of the tiny chunk of volume from the point R as big R minus little r. So we have that squared on the bottom. We then have the unit vector, which is big R minus little r on the top, and the length of big R minus little r on the bottom. That's why we end up with the big R minus little r cubed on the bottom. We then have the ρ dV, which is the charge in the tiny chunk of volume. Then we integrate to get the total electric field from the full volume at the point R. And that equation will look like this.